We continue reviewing force, work, and energy. Here we need to find the acceleration of the system and the string's tension. We've said that whenever we want to find the acceleration of a system, it's often good to consider every bit of the thing as the system. In other words, all 4 kilograms are the system in this case. And when that is the assumed system, the tension in the string is an internal force. It doesn't act on the system. So in a case like this, the net force is simply mg on this 1 kilogram mass, which is 10. 1 times 10 is 10. And that equals the mass times the acceleration. So the acceleration of this system is going to be 2.5 meters per second squared. All parts of the system will be accelerating at that rate. Now we need to find the tension. So it doesn't matter really what we do, but if we assume that now the system that we're focusing on is the 3 kilogram mass, what would the free body diagram look like for that? The normal force and the weight of the thing would exactly cancel each other. So the only force we have is the tension. And so the net force needs to equal the mass times the acceleration. So I think the tension is going to be 7.5 newtons. That's how you do that one. All right, how about the next one? Now we have some friction here, some kinetic friction as this thing slides. So the kinetic friction force, recall, is equal to mu sub k times the normal force. And we do that in our head for this case. What's the normal force on this mass? Isn't it 80? 80 times 0.25 is 20. So there's a 20 Newton frictional force that's acting on this. All right, so let's consider the system as being all of this. What's the net force? The net force is going to be the weight of this 12 kilogram mass, which is 120. Take away friction, because friction is holding us back a bit. And that needs to equal the mass of the system, which is 20, times the acceleration. What's that? 5? Acceleration is 5 meters per second squared. Now we need to find the tension. Doesn't matter which of these we choose to be the system now, but how about if the system is the 12 kilogram mass? If we drew a free body diagram for that, we'd have 120 newtons acting downward, and then we'd have this tension trying to hold it back. That's what the tension in this rope does. 120 minus the tension is equal to 12 times the acceleration, which is 5. How about 60? 60 newtons. That's the tension in that rope. All right, one more. This is an Atwood's machine. Because it's not mentioned, we are assuming that this is a massless, frictionless pulley. So this pulley does not actually rotate. This rope just slides relative to it. If we consider the system to be all of it, what do we have? We have 60 newtons pulling down this way, but only 40 pulling down that way. So I'm thinking that the net force is going to be 20. 60 pulling this way, 40 newtons pulling that way. M times G minus M times G. And that needs to equal the mass, which is 10 kilograms, times the acceleration. So I think the acceleration is going to be 2 meters per second squared. And what about the tension? Doesn't matter which of these we choose to make the system. Let's choose the 4 kilogram mass. Now when we do that, let's draw a quick free body diagram. We're going to have the tension pulling up on the 4 kilogram mass, and M times G for the 4 kilogram mass, which is going to be 40, isn't it? We know the tension is bigger because this 4 kilogram mass is going to be accelerating upwards. So Newton's second law says that T minus 40 should equal the mass times the acceleration. The acceleration we already determined for the whole system was 2. So what's this? 8 plus 40? 48. Tension is 48 newtons.